let's share. Let's go down here. We are, let's see, today we're writing here, 1st of December, 2025. Don't forget the exam is the day after tomorrow, the third exam, chapter 6 and 7, labs 2 and 3, 9:40 to 11:40. We are almost at the end of the semester. Wow, we have just 1, 2, 3 more meetings, four meetings with the final exam. We have 4 more meetings, and then we can take the time off for the winter. See here. Yes, the lab grades are out of 100. Your final grade is going to be there in Canvas. Okay, I'm gonna make an adjustment for lab 3. I already posted. Let me write that down, everything here for the notes. Insert page break. Today, December 01, 2025, Monday. 1. I corrected the reports for labs 2 and 3 and uploaded the correction to your group folder. 2, I logged your grade for lab 2 in Canvas and will log the grade for lab 3 later on. Okay, there will be an adjustment. So I adjusted the notes that I adjusted the grade in Canvas for lab 2. So your grade on the correction PDF file is different from your grade in Canvas. I will do the same for the report for lab 3. Okay. The grade, the lab grade is out of 100 points. Okay. The third exam will be the day after tomorrow. Okay, and what's going to be the chapters? What chapters? Go back there. Chapters 6 and 7, labs 2 and 3. Chapters 6 and 7, labs 2 and 3. Okay. Let's take a look at the materials for chapter 6 and 7. Chapter. Interesting, can't find it. Let's here. That's chapter 8. Yeah, strange, right? He didn't find that. Why is that he didn't find? What about now? Okay, so should be able to find now. That's strange. He didn't find that before. Eight. We want chapter 7. Chapter 7. Here you go. Chapter 7. Chapter 6 and 7. Here you go. Chapters. Yep.
Professor,
Yeah.
there is someone that's trying to enter the Zoom meeting.
Okay, let me check here.
Thank you.
Thank you for letting me know. Let's see here. Oh yeah, Awa is trying to get in. Okay, thank you. This one is restart at 1. The restart at 1. Okay, those are the chapters, the sections of the chapters. Work done by a constant force, work kinetic energy theorem, gravitational potential energy, conservative versus non-conservative forces, conservation of mechanical energy, non-conservative and work kinetic energy theorem, power, and work done by a variable force. And sections 2, 3, 4 of chapter 7. 2, 3, 4 for chapter 7, plus labs 2 and 3. Okay. Last time, let's see what we're doing last time. Okay, we were doing the moment of inertia. Okay, we start doing the moment of inertia of a ring, annular distribution of mass. Okay, so let's that by the way, that's chapters 9, right? Yeah, that's chapter 9, second part of chapter 9. And I also want to look at the sections. Chapter 9. Rotational dynamics. Yep. Okay. Let me write that down. Oops. Let us look at the sections of chapter 8 and 9 that we covered so far. That action and force. Okay, so we look at that force and torque, rigid body in equilibrium. We're skipping 9.3 for now. Newton's second law for rotational motion. Okay, we did that. And then we got to look at rotational work and energy and angular momentum. Let's take a look at chapter 8. Remember, chapter 8 and 9 are not going to show up in this third exam. It's going to show up only in the final. You go chapter 8. Rotational motion and angular displacement, angular velocity and angular acceleration, the equations of rotational motion, uniform rotational motion, and uniform accelerated rotational motion, angular variables and tangential variables, centripetal acceleration, tangential acceleration. We skipped rolling motion, and we kind of covered the vector nature of angular variables. Okay, use right hand rule to find out the direction of the torque, right? Torque and angular acceleration. So those are the two chapters that are going to show up in the final exam. So Newton cycle law, and let's go back here. Oh yeah, we're going to find the angular momentum of the ring. Okay, the angular momentum of the ring. So let's just then, not the angular moment, sorry, the moment of inertia. Last time we were calculating. Last time we determined, right? The moment of inertia of point masses. Okay. And it started calculating the moment of inertia of a continuous mass distribution. Continuous mass distribution. More specifically, the simplest continuous mass distribution is that of a ring. Okay. The easiest is that of the ring. That's the one that's easily calculated. The moment of inertia is easily calculated. Okay, let's see how I'm going to rephrase that. Let me rephrase that. Okay, let's put it this way. It is very difficult to calculate the moment of inertia of a continuous mass distribution. The exception is the ring. Okay. Most of them, okay, because most of them require integral calculus. The exception is the ring. The ring, the moment of inertia of the ring can be calculated using algebra. And go. And there is the reason for that. The reason for that it's very difficult to calculate the moment of continuous mass distribution because most of them require integral calculus. The exception is the annular, right? Mass distribution. But there's more to it. With respect to an axis that is perpendicular that is perpendicular to the plane of the ring and passes through its center. Okay? Not only, to calculate the moment of inertia of annular mass distribution using just algebra, it must be with respect to a specific axis. And this axis is the one that's perpendicular to the plane of the ring, and that axis passes through its center. If you have the case of a moment of inertia with respect to an axis that passes not through the center of the ring, but through the ring itself, that's going to be, you have to use calculus. Okay? So not only it must be a ring, but must be a specific axis with respect to the ring. And let's take a look here. Here you go. Here's the ring. And here is my axis. We want to calculate the moment of inertia with respect to the axis. That's the plane of the ring, right? And this axis is perpendicular to the plane of the ring. On the top of that, the axis is at the very center of the ring. In order to calculate this ring, here you go, just consider several mass elements along this ring. See that each of those infinitesimal mass elements, they are at the same distance from the center of the ring. This mass element is at a distance r. This other mass element is at the same distance r. Okay, so because of the geometry of the ring, we can calculate we can calculate its moment of inertia using just algebra instead of calculus. Okay, so just by breaking down the ring in very small infinitesimal elements, which by the way is going to have the same distance to the axis of rotation, we can come about and find out what's going to be the moment of inertia of the ring. Okay, the moment of inertia with respect to this axis. Let me see. Okay, this thing is not supposed to be here. Okay, so now if the axis would pass through this, would be located exactly at the ring, now each infinitesimal element of the ring would be at different distances from the axis, and it would be more complicated to calculate it. Okay, so that's the challenge that we have when we calculate the moment of inertia of a continuous path distribution. Okay, so here you go. And here's another case too, right? Suppose, let's see, here you go. And here is another case. Here's another axis. Okay, here's another axis of rotation, which I illustrated here. Oh, this one goes here. Here you go. Let me get this one out. Here's another axis of rotation, right? This one right here is the same situation. If we take the distance of each mass element from this axis, we get different distances from the axis, right? The red mass element is at a distance different from the axis compared to the green mass element, and so on. Okay, and to calculate something like that, you are going to need to use calculus. And this ring, I'm gonna get this one here. This ring has a radius r. Yeah, here you go. This ring has a radius r. See the difference? See the difficulty? The challenging, the challenge that because of that I calculate just the because of this mathematical difficulty. What do I do in this course? I calculate only the moment of inertia of a ring with respect to an axis that's perpendicular to the plane of a ring and pass through the center. This we can calculate using algebra. And for everything else, I just tell you what the moment of inertia is. We don't calculate here in the classroom, okay? So you can write down that the moment of inertia during can calculate. The reason for that is because every infinitesimal mass of the ring is masses of the ring are at the same distance from the center of the ring. If the axis were chosen at a different place, then we would need the calculus to determine the moment of inertia. Okay? And how do we do that, right? Well, I already gave you the recipe. Already gave you the recipe for calculating this moment of inertia. Group. I cannot ungroup it. That's so strange. Okay. I cannot ungroup, right? Here you go. Yeah, I think the struggle is there. It's gonna take a long time to do for everyone. So I just stop at this one. And I'm gonna put it with a different color. One is red, the other is green. Let's say this one here is gonna be what? It's gonna be yellow, orange, right? So this is another element of the ring. So you can see that all those elements are the same distance from the center of the ring for the case of the ring, right? So here you go. So from the definition of moment of inertia, we have the following. Let's get our equations placed in there. Okay, I is going to be what? I'm going to write that delta M1 times R1 square, right? Plus delta M2 times R2 square. Plus 1, 2, 3 delta Mn Rn square. Rn square. That's how we write the moment of inertia for any continuous mass distribution. Okay, if we can here write it in a simpler way, in a shorthand way, using a summation operator, right? And when you do that, shorthand, this will be our shorthand notation. I is gonna go from 1 to n. Yeah. Delta mi. But for the case of the axis, right? That's perpendicular to the plane of the ring and pass through its center, this R sub I is going to be the same for every mass element of the ring. So this R sub I can be replaced, R sub I square can be replaced by R square. And when we get the same R for every element, we can take this R square out of the summation sign, and we end up with the net mass of the ring. This term that you see right in here is going to be M. Okay? Okay, now, let us calculate the moment of inertia of a ring with respect to an axis that is one perpendicular to the plane of the ring and an axis that passes through the center of the ring. That's what we're doing right now. And now that we have the summation here, the summation is nothing but the total mass of the ring that I set to be equal to M, okay? We usually here write that with the M in front of the R square, okay? And that's what ends up being the moment of inertia of a ring. But it's not just the moment of inertia of a ring, but it's the moment of inertia of a ring with respect to an axis that's perpendicular to the plane of the ring and pass through the center of the ring. We have to emphasize that, right? Let's see here. Okay, so what would be the moment of inertia of other continuous mass distributions? Okay, so we can look at the moment of inertia of a disk. Okay, axis perpendicular through the plane of the disk and that passes through its center. Okay. In this case, like I said, you need calculus. To calculate that, you need calculus. Right? You need calculus. So I will just give you the result here. For this case, it's going to be half of mr squared. And don't forget of a disk of mass M, and radius R. Axis perpendicular to the plane of the disk that passes through its center. You need calculus as well. You need calculus. And the moment of inertia and the moment, and I is given by, that's what it is. Okay. And what about a uniform thin rod? Mass M and length L. For a uniform thin rod of length L and mass M with the rotational axis perpendicular to the rod and passing through one of its ends. Okay, so if you do the math, you get something like that. We can repeat for the rod, but now the axis of rotation passes through the center. Let's see here. Oh, I'm sorry. This one here is the center, through its center, okay? This one is here through the center. And this one is here through the one of its ends. And then when you do that, here you go. You get something like that, 1/3. Okay? Solid sphere. What about a solid sphere? Solid sphere of radius R and mass M, rotational axis passing through the center of mass of the sphere, which is the geometrical center of the sphere. We get this one right in here. I equal to 2/5 mr squared, and so on, okay? And so on. Let's take a look at the book. The book, there are many other things that, let's take a look at the book here. Let's see what they have there. Which moment of inertia, which different moments of inertia we have, right, for the book. Log in. No, log in. Okay, so physics 6, this one. The Wiley course, right? Resources. Launch the book. And we are going to go for chapter 9, rotational dynamics. Rigid object in equilibrium, center of gravity. Let's see if we have moment of inertia here. Okay, we have to go through one by one here. Let's see if they document the moment of inertia for each of those. Some books do that. Center of gravity. Moment of inertia right in here. You go moment of inertia of a body. You go exactly what I put in there. that I did that for the ring, right? Okay, here you go, right in here. Moment of inertia for various rigid objects. Seeing hollow, cylinder or hoop. Hoop is the ring, right? Seeing solid cylinder or disk, half mr square. Here's the axis. In this case, here's the axis, 112 ml square. If the axis at the end of the rod is 1/3, for the case of the sphere, the axis passing through the center of it is 2/5. But now if the axis passes through the edge of the sphere is 7/5. Note, see that this one is greater than this one. And also this one is greater than this one. This is no coincidence, okay? This is no coincidence. When the axis passes through the center of mass of the object, you end up getting a smaller moment of inertia. Here is the thin-walled spherical shell, not a solid shell, but not a solid sphere, but a spherical shell. 2/3. 2/3 here, 2/5 there. Okay? This one here is greater than this one here. Seeing rectangular sheet, okay? 112 ml square. Don't forget, it's a rectangle. And it doesn't matter what's this size here. What matters is this length here, perpendicular to the axis. Okay. Again, note C. For the axis passing through the edge of the rectangular sheet, the moment of inertia is larger. Okay. Again, this is no coincidence. This is no coincidence. And now that we have the moment of inertia, we can start calculating some interesting problems. Two particles thin rod. Okay, so let's take a look. Here is true is the problem of point particles, right? Point particles. And we have two situations. Here you go. We have 2 point particles attached at a rod. Mass are attached to the ends of a massless rigid rod. The moment of inertia of this object is different depending on whether the rod rotates about an axis. We did something similar, right? Here in the classroom. Like just a slightly different problem because we chose the baton. And we took different axes of rotation. Okay. Torque, let's see if we can do this one here. Yeah. And now that I mentioned that to you about the moment of inertia, and the most important thing that you have to remember about the moment of inertia is that it is the angular counterpart of the linear mass. That's what you have to remember. And now I'm going to update our table comparing our linear quantities with the angular quantities. Okay, so right in here, going back to my notes, and so on. Here you go. Okay, let's see, moment of inertia is the angular counterpart of the mass. And then there are other parameters also that we covered in in those previous chapters. In the previous chapter, just remember that the previous chapters we were dealing just with point masses, okay? Let me write that down here. Recall that in the previous chapters, 1 through 7, 1 through 7, comma, we were dealing only with point masses. Okay? Chapter 8 introduces you to a mass distribution. Which, by the way, the mass distribution. An important thing to remember, an important thing to know is that a solid object behaves as though all its mass is concentrated at its okay geometrical center. In the case of a solid sphere, right? The motion of a solid sphere, the translational motion of a solid sphere, can be modeled as though all the mass of the sphere is concentrated at this center. Okay, for instance, okay, the translation of a solid sphere can be modeled of a solid sphere having a uniform mass distribution, can be modeled as though all its mass is concentrated at its center. Okay? The same thing applies with a rod and other mass distributions. Okay? So going back to what we have here. Okay, so here you go. And now we can extend the concept of work, for instance, of a point particle to that of a rigid object. If work is going to be linear force times displacement, for the angular counterpart of the work is going to be the angular force times angular displacement. Okay? It's not difficult to memorize that. For the case of the kinetic energy, we have half mv squared, and all of that can be proven mathematically, okay? For a point particle that has a kinetic energy half mv squared, a rigid body is going to have a rotational kinetic energy that's going to be half of the angular mass times the angular velocity squared. The unit here is joules. The unit here is joules as well. The work kinetic energy theorem. Okay, the work kinetic energy theorem is the difference between the work done by the net force, right? Is going to be given by the difference in kinetic energy, final kinetic energy minus initial kinetic energy. Similarly, the work done by the net torque applied to a rigid body is going to be the final rotational kinetic energy minus the initial rotational kinetic energy. In the case of the momentum, which is mv, now the same thing that we have the same thing for a rigid body. The angular momentum, which we represent by the letter L, is going to be the moment of inertia times the angular velocity. And that's the vector angular velocity, which is given by the right-hand rule. Okay? Conservation of momentum. Well, we do have conservation of momentum when the net force is equal to 0. For the rigid body case, we do have conservation of momentum when the net torque is equal to 0. Okay? So now the initial angular momentum is going to be equal to the final angular momentum. Newton's second law. F net is ma. For a rigid body, net torque is I times alpha vector. Okay? And then the mechanical energy, we have the same thing. Kinetic energy plus potential energy. In this case, we are going to have the translational kinetic energy plus the rotational kinetic energy plus the potential energy of the center of mass of the rigid body. Okay? So we can extend in a rather straightforward way. Okay? Let's take a look at let's take a look at an example. An interesting example that uses conservation of angular momentum. Okay, it's the case of a skater. Let's see if I have an illustration of the skater here. Oh yeah, that's the case here of the skater. Okay? You have seen those guys performing maneuvers, right, in the ring. And let's say this skater has his or her arm extended, right? And is rotating about an axis that passes through the length of his body. Have you ever noticed that whenever he contracts his or her arm, what happened to the angular velocity? Check that out, right? Let's see if we can see something like that in the internet. Skater rotating about an axis along his body. Let's see if we can have something like that I want to see a rotational dynamics of an ice skater. Yeah, let's take a look at this one. Let's see.
O que temos aqui é uma patinadora no gelo girando a uma velocidade angular inicial lenta ômega e suas mãos estão estendidas.
Notice that this skater here has the hands extended as well as the leg as well, right?
Agora, quando ela puxa os braços e as pernas.
Now, when she contracts the arms and the legs, what happens to the angular velocity? It increases, right? And it has to do with the conservation of angular momentum. Okay? Let's see if you have another one here.
So, have you ever noticed how an ice skater spins faster when she pulls her arms in?
Here you go.
What really is the secret behind this? So, by the end of this lesson, you'll uncover the physics behind this.
Let's play it again.
So, have you ever noticed
this lower angular rotation
faster,
and then she contracts her arms?
What
right?
Really
and the angular velocity
so
increases.
By the end of this lesson,
there's a reason for that.
The physics.
Okay, there's a reason for that. Why does it happen? It happens because at this point here, when the arms are extended, the moment of inertia is greater if the let's say the initial moment of inertia is greater than the final moment of inertia. You have masses, more masses further away from the center of rotation, from the axis of rotation. That's why the moment of inertia is greater, okay? When you contract, when the skater contracts its arms, it decreases its moment of inertia. And we can, here you go. We can look at that here in this problem. Ice skate is upright and is rotated about an axis that passes through her body. The skater has only rotational motion, and her arm are extended with initial moment of inertia I naught. What happens to the angular velocity of the skater if she contracts her arms, decreasing her moment of inertia to IF, okay? The initial angular velocity is known to be W naught, omega naught, okay? Keep in mind that the net torque applied to the skater is zero. There is no force making the skater rotate, right? There's no force, no tangential force applied to the skater to make he or she rotate, okay? Because the net torque applied to the skater is zero, comma, we must have conservation of angular momentum. Or, pick up, just like we did for linear momentum. Final angular momentum is equal to initial angular momentum. But going back to our equation for angular momentum is angular mass times angular velocity, okay? Final angular mass times final angular velocity is equal to initial angular mass or moment of inertia times initial angular velocity. We can solve it for the final angular velocity. Okay? Because I naught is greater than IF, it means that omega F must be greater than omega naught. Okay? And again, I naught, I'm going to repeat here, right? I naught is greater than IF because, oh, hi. Because when the skater has her arms extended, comma, some of the masses, some of its infinitesimal masses are further away from the axis of rotation, making its moment of inertia greater than the moment of the final, making the initial moment of inertia greater than the final moment of inertia. Okay? We cannot, it's very difficult to calculate the moment of inertia of a human body, okay? But you can have a good qualitative idea of the comparative moment of inertia in those two situations, right? In this situation here, you know, this part of his arm, let's say either the same distance from the axis of rotation, compared to this case here, right? But the very tip of his arm, his hands, let's say, right, is at a larger distance than his larger distance from the axis of rotation if compared to the tip of his hand with the arms contracted, right? For this reason, this moment of inertia here must be greater. The moment of inertia in this situation must be greater than the moment of inertia in this situation. Okay? That's how we analyze in a qualitative fashion the moment of inertia of a skater, a figure skater. Okay, so now we finish this chapter here. I want to take a break with you right now. Okay, so break. (10:40). Do you have any questions? 10:55 a.m. And then we can start covering chapter 10 once we return from the break, okay? Now here we go, 10:41, right? Now it's 10:41 to 10:56. Okay, so I see you in 15 minutes. Thank you for being here. We'll talk soon. Let's record and let's share the screen. Okay, 10:56, and then we're going to start now chapter 10. Let's take a look at chapter 10 here. Simple harmonic motion and elasticity. You have all those sections, ideal spring and simple harmonic motion. There's a reason why we study simple harmonic motion. And the reason that we study simple harmonic motion is because this type of motion can be used in timekeeping devices. That's why timekeeping is a very important activity because of more and more precise devices capable of keep time. We have been able to navigate to distant parts of the world. Okay, so here you go. Why do you keep time? Why do we study a simple harmonic motion, right? Well, because it has several important applications in real life. The most obvious one is being a way of keep time. We can use simple harmonic motion to build very accurate and precise timepieces. Examples, right? One important example is the physical pendulum used in the grandpa clock. Everybody, hopefully you have seen that before, right? The grandpa clock. I used to have an uncle that had one of those grandpa clocks. Let's see. No, that's not at all. Grandpa clocks. I don't want grandparents. I want grandpa clock. Here you go. Yeah, here you go. One of those grandpa clocks. No, nowadays this type of device is. Oh, that's not what I want. Has been. Here you go. Let's see if I can get that. We have a pendulum right in here, right? The tip of the pendulum. It was revolutionary when people managed to invent a mechanical clock that used the pendulum. It was kind of revolutionary at the time. And that's one of the reasons. And this type of pendulum, they undergo what we call simple harmonic motion, okay? And in addition to the pendulum, there are other ways of performing simple harmonic motion. One of them is just by attaching a mass to a spring, okay? Grandpa clocks. Simple harmonic motion can be reproduced in different ways. Let's see, here you go. One, by attaching a mass to a spring, by extending the spring and let the mass oscillate as time goes by. That's one way of reproducing a simple harmonic motion. Another way of reproducing simple harmonic motion is by attaching a mass to not a spring, but a string, to a very light string. Let's put it this way, very light string, disturbed from its vertical position and let it oscillate. Okay. Another way would be by using a rod which is left to oscillate from one of its ends, one of its extreme. Okay? So 3 different ways of reproducing simple harmonic motion, but there are others. Those are just mechanical ways of reproducing simple harmonic motion. There are other less obvious ways of reproducing simple harmonic motion. Okay? You can also use electronic circuits, electrical/electronic circuits. That behave in a simple harmonic motion way. Okay, that's another way. Atoms oscillation, the oscillation of atoms, by monitoring the oscillation of certain atoms. So those are the fancier way. So much that nowadays we have clocks that use that the oscillation of atomic clocks. Let's use here atomic clocks, right? That use the oscillation of some atoms. Okay, atomic clocks are the world's most accurate timekeeping devices. So look how far we have gone, right? We started with older clocks that, for instance, one of the older clocks used a rope that you'd let burn as time would go by. Okay, we also have the hourglass that could be used as a timekeeping device as well. And then we start using mechanical clocks that didn't use the pendulum. Eventually, someone very smart called Christian Huygens managed to build a mechanical clock that used a pendulum. And that was a huge improvement at the time. It was back during the age of the discovery. Christian Huygens was a Dutch scientist who kind of appropriate Galileo Galilei's idea and used a pendulum to create a very precise mechanical clock. So we at the time of Christian Huygens, they already had mechanical clocks, but they didn't have mechanical clocks that used the pendulum. So when Christian Huygens came with this invention of his of using a pendulum as an element to help to keep time, he attached that pendulum to existing mechanical clocks. Okay. After the mechanical clocks, then we had the clocks that use the electrical current to keep time. And finally, we came to the point that we start using atomic clocks that use the oscillation of atoms, commonly the atom cesium. They work by using microwave radiation to cause electrons in atoms to transition between specific energy levels. The frequency of this radiation is then counted to tell time. This precise method makes atomic clocks crucial for technologies like GPS and scientific research. So that's how far we have gone with measuring time. Okay. And the oscillation of certain atoms, such as cesium. You can all visualize those three, right? What is difficult for you to visualize right now is those other two here. But the principle is the same. They all use simple harmonic motion to keep time. Let me just put something here about the pendulum, right? There are several ways to create this type of motion. One of them is by using a pendulum, a very important element that was used by Galileo Galilei and Christian Huygens to create very accurate and precise timepieces. It was because of this invention, using a pendulum, that we were able to navigate the oceans during the age of discovery between the 1400s and the 1700s. First was the Portuguese, then was the Spanish, then was the Dutch, and then was the English. The age of discovery started with the Portuguese in the 1400s and ended with the English that became the superpower of the time. The Portuguese were also the superpower of the time, okay? The age of discovery started with the Portuguese and ended with the English. It was because of this type of device that we were able to navigate to the distant parts of the Earth and keep track of the position of the ship, okay? So I already mentioned that another way of creating simple harmonic motion is by attaching an ideal spring, stretch it, attaching a mass, right, to an ideal spring, stretch it, release it, and let it move. Let's see if I have a simulation here of this type of situation. Simple harmonic motion right in here. Okay, so you go, simple harmonic motion. A mass, this mass is in the horizontal direction, attach it to a spring. Okay, this mass is assumed to be sitting over a frictionless surface. I am taking this mass out of its equilibrium position by applying an external force. In this case, it's my hand. Right? And then I release it, right? I'm extending even further, see that? I'm extending even further the spring. Now, The moment I release the mass is going to accelerate to the left. I extend the spring to the right. The initial velocity is 0. Notice that right here. Let's make this thing larger. View. Zoom, let's see. 100. What about 150? Better, right? Friction is negligible. Frictional forces are negligible. In the next step, the mass is moving towards the equilibrium of position, right? We still have elastic force applied to it. The velocity is building up. The acceleration is also building up. Sorry, the acceleration is not building up. The acceleration is decreasing, right? So maximum acceleration is when I release the mass. Maximum acceleration is when I release the mass because it is at this position where the force is larger. Velocity is 0. Displacement is maximum. Maximum displacement, maximum force, maximum acceleration. Velocity, speed is minimum, is 0. Speed is building up, acceleration is decreasing, right? It was initially larger. The force is also decreasing, and the displacement is decreasing. When it passes through the position of equilibrium, the displacement is going to be 0, the force is going to be 0, the acceleration is 0, and the velocity is maximum. Okay? So it overshoots the position of equilibrium, and now the force of the spring changes direction as well as the acceleration. Not just the acceleration, the spring changes direction, but also the displacement changes direction as well. The displacement was to the right or positive, and now it becomes negative to the left. I didn't illustrate the displacement here. The velocity now is decreasing. The acceleration is increasing. The force is increasing until the mass achieves maximum displacement and the velocity becomes 0. The mass is momentarily at rest. Then it's going to oscillate on the other direction now. Now the acceleration inverted direction, right? Is maximum. Now it's to the right, and it's going to repeat the motion. Okay, that's how. And again, this is the situation of the case in which frictional forces are negligible, right? We're playing the movie here. That's how it looks like in real life. And it is this type of motion that we can use to create timekeeping devices. Okay. So you have to recall how the force, the elastic force behaves. Okay, recall that the force applied to a spring is given by Hooke's law. And then let me put between quotes here. It's not exactly a law. Minus kx. K is the spring constant. And let's not forget that the potential energy, we saw that before in the previous chapter, right? Is equal to half kx squared. If there are only conservative forces applied to a mass attached to a spring, only conservative forces, right? We will have conservation of energy and conservation of mechanical energy, right? Let's put it this way. If we introduce friction in there, then we won't have conservation of mechanical energy. So this relation here will be conserved. If it, I can even, here you go, half mv squared plus half kx squared. The key here is to find out how x and v will vary with time, okay? And by the way, there is a very close relationship between simple harmonic motion and uniform circular motion, by the way, okay? The key to find out how x varies with time, what's the key? You can find this equation by referring to the equations of motion of an object undergoing UCM, uniform circular motion. The equations for the position, velocity, and acceleration along the x-axis of an object undergoing UCM coincide with that of an object undergoing simple harmonic motion. And now that's the moment to be reminded of the equations of motion of the object undergoing uniform circular motion, right? So recall that what we had before, was something like the following, you know. That's what we initially have, right? If you go back to uniform circular motion, let's take a look at the equations for uniform circular motion. Uniform circular motion. We got lecture, go. Let's see if we have writing here, right? Vt over r. Let's see if I can get everything at once. It's just one of the coordinates. Let's see. I'll copy this one, paste it next to this one here, copy it, and delete, right? X, V, and AX. I'm gonna put everything together here. Paste, copy, and delete. We're going to need all those equations. It's just the X component that we need, because the simple harmonic motion in this case is going to be a one-dimensional type of motion. Here you go. Now we have it. I put omega t, but that omega t is in reality v over r, where r is the radius of the circle, right? So that's what the simple harmonic motion is going to look like. But even more important, what you see right in here will have to be replaced with something else. Something else that is related to K and the mass of the particle. Okay? It's possible to prove mathematically, and again, in order to prove that, we need calculus again, differential calculus again. Okay? For simple harmonic motion, the x is going to look like that. It's going to look like that. The v is going to look like that for simple harmonic motion. And the acceleration is going to look like that. Remember, I'm not deriving that. I'm not deriving that because we need the advanced math to do something like that. I'm just doing a parallel between simple harmonic motion and uniform circular motion. Okay? there is more. We can come up with this V that you see here is going to be the maximum velocity of the mass. Okay. When sine is exactly, this sine is equal to 1, right? So we reach the maximum velocity. Let's put here max velocity. Uh-oh. Max velocity. And there is one more thing that we can do about this maximum velocity. This maximum velocity is related to this x naught here. And is related to this x naught by this term that you see right here. X naught square root of km. Okay? This term that you see right in here, has units of 1 divided by second. So when we multiply this term by something that is measured in meters, we get something else in meters per second. Okay? And we have something similar for the acceleration. Okay, what you see here for the maximum value of the acceleration is going to be x naught k over m. And it is possible to find out what this maximum acceleration is going to be, right? Just using Newton's second law of motion. Let's do that. Just use Newton's second law of motion. Remember that Newton's second law of motion is F equal to kx, right? That's what it is. The maximum force is going to be k times maximum displacement. This maximum displacement, it is what I call x naught. Okay? But let's not forget that maximum force is also equal to m times maximum acceleration. Newton's second law of motion. Okay? Consequently, this maximum acceleration that you see here, let's put it, don't put centripetal, right? We gotta put maximum here. Here is not centripetal. Centripetal applies just to the UCM motion. Yeah, that's right. Here we keep acentripetal because we are referring to UCM, okay? For UCM motion, for uniform circular motion, we have okay. For SHM, we have okay, the R is replaced by the X naught. R is the radius of the circle. V over R is replaced by K of square root of K over M. This A max here can be written down, can be found out to be related to the K and M and X naught by using Hooke's law. Okay? K over M X naught. The maximum velocity, we can also find out what the maximum velocity is, okay? We can find out how to find this term here. Actually, we can do that by using conservation of energy. Let's do that. Here you go. How to find Vmax, right? There is a way. There is a way to find Vmax as well using conservation of energy. Right? Let's do that. So you don't have, so you have a way to find out how to derive this thing, right? So how do we do? We do it in the following way, okay? So here go. Consider the initial mechanical energy as being this one right in here, okay? Being this one right in here. Potential energy plus kinetic energy at this point must be equal to potential energy plus kinetic energy at this point. Remember that the acceleration is going to be 0, but the velocity is going to be maximum. Because the force of the spring is going to be 0 at this point, okay? As it overshoots this position, the force is going to work against the velocity. So the situation is going to be like that. Here you go. According to the equations of conservation of energy, mechanical energy at T equal to 0 must be equal to mechanic energy at the X equal to 0, at the position of equilibrium, okay? See the difference here, X and T? Mechanical energy at T equal to 0 is going to be what? It's going to be kinetic energy is going to be 0. Okay, let's put that here like V naught, right? And let's put this one as X naught. And then we do the same thing for mechanical energy at X equal to 0. Equal at X equal to 0. We are going to have maximum velocity. And we are going to have X equal to 0, right? And we simplify those two equations. The mass is being released from rest. And now at X equal to 0, the final mechanical energy, right? The mass is passing through the position of equilibrium. Let's keep on doing that. Use conservation of mechanical energy. The principle of conservation of use the principle of conservation of mechanical energy, which is this next step. Here you go. I'm gonna T equal to 0 is half kx naught squared. At E, at the position of equilibrium, is going to be something like that. Then we want to write Vmax in terms of the rest things that you see here, right? So what gets simplified? Half gets canceled, half gets canceled. Mass goes to the other side of the equation. And then we have to take the square root of both sides. Here you go. Now, do you see how I got it? Right? Now, all you got to do is max. Oh. Max. Oh, it's not x naught square, right? It's x naught because the x naught goes inside the square root. So that's how we calculate the Vmax in terms of x naught and the maximum acceleration in terms of x naught as well. Okay, so in summary, summarizing, the maximum velocity is found by using conservation of mechanical energy, and the maximum acceleration is determined using Newton's second law of motion. Right? Here you go. And here you go, all three equations put next to each other. Here you go. In a different format, right? You have x naught, and x naught. You have positive sign, negative sign, negative sign. You have the term k over m raised to the 0 power, right? When you raise this term to the 0 power, it becomes just the number 1. You have the term k over m raised to the half power. You have the term k over m raised to the first power. And then we switch the cosine to sine, the sine to cosine. Okay? Can you remember that? That's a very good way of memorizing it, right? Positive, negative, negative, power 0, power half, power 1, cosine, sine, cosine, sine, and cosine. The argument is exactly the same for all the three equations of motion. All three equations of motion, right? Let's put it, equations of motion next to each other. So don't forget, that's the equation of motion for simple harmonic motion. And that's the situation that we have now. We covered the ideal spring, we covered the simple harmonic motion and UCM. And we also cover energy in simple harmonic motion, right? But let's continue covering this, the energy of simple harmonic motion. Let's see what else we can get from it. We start with the main equation for the mechanical energy. Okay, that's the main equation for the mechanical energy. And then we replace the kinetic energy and the potential energy with their respective equations. One half of mv squared, the other half of kx squared. And now we have to replace the v here. Oh, well, the first thing that you do is to put the half in evidence, right? Let's put the half here in evidence first. And now we are going to insert the v right in here. We are going to insert the x right in here as well. Okay, we found what the v is. I'm not going to use this one. I'm going to use the other one. Here you go. You know what? Let me copy everything at once, so you don't have to come back here. Negative sign. Okay. negative sign. Here you go. Look at the square root here. Let's see if we have it. Okay, this square is in the wrong place. Let me undo it. No, the square is not in the wrong place. Huh. Oh yeah, here you go. Yeah, the square is not in the wrong place. Okay, good. Oops. Yeah, the square is in the right place. Let's go to the next one. Next stop. This negative sign is going to cancel, right? X naught is going to be squared. This square root is going to cancel because we're squaring a square root. And the sign is going to become sine square. Everything here, now we do not have, okay, don't forget that this parenthesis here is for the half, right? And we do the same right here. Take the square of the negative number, it becomes positive. Take the square of x naught, becomes x naught square. Take the square of km, becomes k square over m square. And the cosine is squared as well. And everything that you have right in here becomes that. Okay? And now we have some common elements here, right? Common parameters here. Let's see. But let's simplify first. The m cancels out with the m. The k, there's something wrong here. There must be something wrong here. Let's see here. Kx squared. Let's see, mv squared. Let's see here. Mv squared. There's something wrong here. Did you pick up any mistake while I was doing that? Mv squared, right? Oh yes. Okay. Okay. So what was the mistake that I made? Nobody noticed that, right? Even I didn't see that. I copy and pasted the wrong the wrong thing. I copy and pasted the acceleration instead of the position, right? I should have the place. I should have the substitute the position here. Okay, you're supposed to be the position. That's why I was getting something strange that was not recognized. So that's the one that should go in there. Okay, right in here. See, I put the acceleration instead of the position x. Okay, so here you go. Now we're going to get the right thing. The right, let's see here. Okay, x naught square, cosine square, square root of km times t. M cancel out with m. And now we are going to have common factors here. This one goes away, right? Kx naught square, kx naught square. See that? Something nice is going to happen, and we're going to see. Here you go. I'm gonna put this guy in evidence, okay? Even better, I want to put this one right in here, kx naught square, so it becomes more obvious. So now I erase that and paste here. This one should be erased as well. And look what we get. We get sine square plus cosine square. Sine square plus cosine square is going to be 1, right? Here you go, number 1. And the mechanical energy is going to be equal to half kx naught square. which is the potential energy at the instant of time equal to 0, right? Which is equal to the potential energy at t equal to 0. Because, kinetic energy at t equal to 0, right, is equal to 0, right? Let me put all of that between parentheses here. So it makes sense, right? It makes sense. Okay? So here we go. E equal to that. Can you remember that? Half k amplitude square, which is, by the way, is a constant. K doesn't change. X naught is always X naught. Doesn't change. Now we can do an example. So you can see how we can use it, this knowledge, to solve problems. Example 1, an object of mass m is attached to a spring of constant k. If its initial position and velocity are known, now we have a situation in which we have an initial velocity. Okay? Find the particle's velocity at the position of equilibrium. Okay? Now we have a situation in which I'm going to illustrate that for you. Okay, so here you go. The situation is like that. The situation is, we have an acceleration from the right to the left, and we are going to have a velocity, initial velocity, from the right to the left. That's the situation of this problem. Okay? Time t equal to 0. I don't need this guy here. T equal to 0. Let's put it here. T equal to 0. Oops. Not capital T, but lowercase t. Like that. Like that. And then he's asking, let's see. I'm going to put another slide here. Example. Let's see if we need that. Example. We want to know what will be the velocity when the mass pass through the position equilibrium. Okay, what's going to be the velocity of the mass when it passes through the position equilibrium? I'm going to put it a little bit more to the right. Oops, this one was supposed to go to the right as well. Like that. The acceleration is going to be 0. That's the initial situation. That's the final situation. Okay. Let me put this velocity here a little bit more to the right. Yeah. I'll copy this one, paste there, and make it the arrow shorter. Like that. Okay. Mechanical energy here must be equal to mechanical energy here. Oh, no, not this one. mechanical energy here must be equal to mechanical energy here. Okay? So let's do that. We're gonna have our break very soon. Let's solve this problem first. Initial mechanical energy is equal to final mechanical energy. Initial kinetic energy plus initial potential energy is equal to final kinetic energy plus final potential energy. Like that. But let's not forget that the final potential energy at the equilibrium position is going to be 0, right? That's why I put 0 here. And remember that my initial velocity right now is not 0. Unlike the other one, right? The other case. Here's a case in which the initial velocity is not 0. And what are we trying to solve here? If it's initial, find the particle's velocity at the position of equilibrium. So you want to find this velocity right in here. We can cancel out the half, simplify, simplify, simplify. Pass the mass to the other side. Okay, this is going to be divided by m. Oh, divided by m. Divided by m. Like that. We no longer have an m here. This m over m goes away. And then we get our final velocity. As being, I'm going to write the final velocity here on the left side. Just put the square root. All right, here you go. That's what we get for the final velocity. And by the way, it can be either positive or negative, depends where the particle starts, right? If the particle starts on the extreme right, the velocity is going to be negative. If the particle starts at the left side, left to the position of equilibrium, the velocity is going to be positive. Okay, now we're going to do something else, right? So here you go. Let's play the movie again, right? We're going to play the movie. That's time t equal to 0 at equilibrium position. We're going to put it like that. Here you go. At equilibrium position, at the position of equilibrium. And then the particle is going to overshoot. And I'm going to copy what I had before there, so I don't need to do it from scratch. Yeah, right in here. Right in here. That's the one I want. Okay. And now we have velocity is going to be equal to 0, right, at this position. And I want to illustrate the x final. Not x naught, but x final. This x is gonna be, oh, wait a minute. Something wrong here. Yeah, all I want is this guy here. Okay. Okay, and this one is going to be my X final. XF. Like that. And I'll put black color to be consistent. I don't need that. At the position of equilibrium. At maximum displacement. Maximum displacement from the origin. See the spring here completely, right? The spring here is stretched. And by the way, let's make it more realistic. Let's compress even more the spring. The mass is going to be a little bit more to the left, and the displacement here is going to be a little bit more to the left. Okay? Like that. So the initial situation is this one here, and the final situation is this one here. Mechanical energy at this point must be equal to mechanical energy at this point here. Okay? I'm going to make this force a little bit longer, denote it stronger, right? When we make it longer, we are denoting that the force is stronger. That's what this new here you go. Example, this other example is all about. Here you go. Repeat the above for the position of the particle at maximum amplitude. Maximum amplitude corresponds to V final equal to 0. We start to do everything that we did before. Let's see. I'm even going to copy what I did before. Here you go. Initial mechanical energy is equal to initial final mechanical energy. I'm going to even copy this one as well. With here you go. Initial mechanical energy, go to final mechanical energy. Initial kinetic energy plus initial potential energy is final kinetic energy plus final potential energy. We get mv naught square kx naught, but now it's no longer the position of equilibrium. So we have to put final, right? Half of final, half of kfx final square. We want to find this guy here. Let me emphasize that. The first simplification means that we have to cancel out the half. Okay? Because the particle is at the other extreme, this V must be 0. Okay, this one doesn't isn't that fine in this case? In this case, final velocity will be 0 because the particle is at the very end of the compression. of the spring, right? So we have, let me write that down here, 0 here. We're squaring the 0. This term disappear. We pass the k to the other side. M over k. Oh. M over k. The k cancel out with k. We are almost at our break point. Oh, by the way, since I passed the k to the left, I don't need to have a k right in here, right? Then we take the square root. X final. Take the square root of all that stuff. Okay, and now we can have our break. Any questions about that? So those are the type of problems that you can solve. Energy in simple harmonic motion. The next topic is going to be here. Ideal spring, simple harmonic motion, and UCM, energy and simple harmonic motion. The simple and physical pendula, all right? And sections from 10.5 to 10, we will skip it. Let's stick just with those 4 sections here. Okay, and the break 10, is it 10:50? No, 11, right? 11:56, 11:57. 57 a.m. to 12 p.m. Right? Any questions about that? Okay, I see you in 15 minutes. So we're recording, and let's get our this one here. We want this one right here. Okay, energy. And now we are going to talk about the simple pendulum and physical pendulum. Simple pendulum and physical pendulum. Okay. I want you to understand that the mass attached to a spring is the ideal type of simple harmonic motion. Okay. Now, the simple pendulum is just an approximation of the simple harmonic motion, right? And the same thing applies to the physical pendulum. The simple pendulum and the physical pendulum are just an approximation, okay? And the physical pendulum are just an approximation to simple harmonic motion. Okay, the mass attached to, and I'm going to be even more specific here. The spring must be an ideal spring. for you to have simple harmonic motion is a mass attached to an ideal spring and put to oscillate is the case of simple in the case of simple harmonic motion. Okay. The simple pendulum and physical pendulum, they're not exactly simple harmonic motion, but they are a good approximation for the simple harmonic motion. There's a reason for that, okay? But which we are not gonna get into. And despite of being an approximation to simple harmonic motion, the physical pendulum have been used as engines, right, for timekeeping. Though both the simple pendulum and the physical pendulum, they are very good devices that keep on oscillating back and forth. Have you ever noticed that? There is very little friction, so they oscillate for a very long amount of time. Okay, so let me tell you what the simple pendulum looks like. The simple pendulum looks like that. A string with negligible mass, length L, attached to a mass. We can neglect the mass of the string. When I mean neglect the mass of the string, I mean that the mass of the string is at least 10 times less than the mass of the bob, of the particle, right, that we put there at the end. And that's what this thing means here. That's what the simple pendulum is. The physical pendulum is just like your grandpa pendulum. Here you go. The physical pendulum is this one right in here. Is any rigid body suspended by a point of oscillation. This rigid body has a center of mass, which is a point where all the mass of the object is concentrated. Okay, and it's put to oscillate back and forth. So that's the grandpa clock, right? The grandpa clock is a physical pendulum instead of a simple pendulum. Okay, so here you go. We can use physics to find out the equations of motion of a simple pendulum. Okay, so let's do that. Let's do that how, and you're going to understand why the simple pendulum and the physical pendulum are undergoes motion that is an approximation to the simple harmonic motion, and that's a better way of writing that down, right? So a simple pendulum, the motion of a simple pendulum and the physical pendulum is just an approximation of the simple harmonic motion, although a very good one, like that. Okay, so let's study the simple pendulum. In the case of the simple pendulum, is a small object of mass m attached to a spring of length L and negligible mass. Lowercase m. Big case m is much larger than m, and the largest size of the object that is attached is much smaller than the length of the string. Okay, let's go back here. Here you go. See, let's say I put a bob here, diameter d. In order for this thing to be considered a simple pendulum, this d must be less than 10 times less than L divided by 10, right? 1/10 of the length of the distance between the point of rotation to the center of mass of the mass. Okay. So in order to model this type of motion, we gotta come up with the free body diagram. And that's exactly what I have here. Look at the forces acting on the simple pendulum and the mass, right, of the simple pendulum. And you're going to see that we have the weight and the tension, nothing else. What you see right in here is just the velocity of the mass. And then we can come up with the in order to find out the equations of motion of the simple pendulum, we have to find the net torque applied to it. Let's do that. So here you go. Here, net torque is the torque of the tension plus the torque of the weight of the pendulum. The torque of the tension, going back here, the tension, but this the torque with respect to this point here, to this point of rotation. Okay? Remember that the mass is oscillating with, that's the axis of rotation of the mass. The torque of the tension is going to be zero because it is because it points towards the point of rotation. It doesn't have a torque at all. But the mass, the weight of the pendulum, it does realize a torque. Okay, it does have a torque. Let's see here. I have the axis X and Y. Let's see if I have everything that I need. I can put my axis there at the point of rotation. It's better if you do that. Okay, here you go. And let's not forget that this mass makes an angle theta with the vertical. Okay, if this angle here is theta, it also means that this angle here is going to be theta. Okay, this force is parallel to the vertical direction, and this line coincides with the other line there. Okay, so this angle here must be theta. Consequently, the torque of this weight is going to be mg L sine of theta. MGL sine of theta. Okay, so I have it here already. MGL sine of theta, and there is more. There is more. My positive theta, my unit vector theta, is in the counterclockwise direction, whereas my torque is in the clockwise direction. Consequently, we must have a negative number right in here. We are measuring the angle theta in the counterclockwise direction, right? And the torque is in the clockwise direction. Consequently, we must have a negative sign right in here. And now that we have this equation for the net torque, we can apply Newton's second law for the net torque. Okay, Newton's second law for the net torque is going to be, net torque is equal to moment of inertia of my point mass times the angular acceleration, like that. And I'm going to do the following. I'm going to put this L right in here so you are not confused about it. And I'm also going to put a parenthesis. Okay, so there is no doubt that we are taking the sine of theta. I'm going to do the same here. Like that. Looks better. But the moment of inertia of a point particle, you should know what the moment of inertia of a point particle, right? The moment of is mass times the distance of the particle from the point of rotation. So here you go. Is mass became L square, the length of the string. And that will be this one here. Let's see. Yeah, this one I forgot to erase, right? I have to erase it now. Yeah, otherwise we're going to have L squared there. So there is some simplifications that we can do. Emma, oh, wait a minute. Let's see if I did something here that I was not supposed to do. Okay, yeah, here you go. That's what I wanted. ML square. I had erased this, ML square is I, right? And now I'm gonna copy that and paste right here. M is gonna cancel out with M. L is gonna cancel out with L. Okay. And my angular acceleration ends up being something like that, like the following. Something like that. Okay, minus G over L sine of theta. From the above, we cannot easily find the angular velocity or the angular position. However, we can apply an important approximation to this equation. Okay, and we will be able to do both. Okay, so here you go. What is this approximation? The approximation is the approximation for small angles. When we put a pendulum to oscillate, we always displace it, make a very small displacement from the position of equilibrium. And this angle can be less than 10 degrees, okay? But the small angle approximation can be up to 45 degrees. Up to 45 degrees, you get only 11% error, okay? Up to 45 degrees. But we usually, displace the pendulum less than 10 degrees. The approximation is for small angles. By small angles, I mean something that provides less than the 11% of error for angles up to 45 degrees. So the small angle approximation is this one right in here, where sine of theta is approximately theta. And I can prove that to you, okay, by using a spreadsheet. Let's do that. If you don't believe this approximation, I think it's very instructive to take a look at that. Here you go. I don't think I did that before, right? Small angle approximation. Okay, here you go. Small angle approximation. Angle approximation. View, I want to zoom. Yeah, here you go. Like that. Theta. First, I'm going to put theta in degrees. Then I'm going to change it to radians. Superscript, here you go. Symbol. Like that. And I'm going, here you go. And now I want to put the theta, not just in degrees, but in radians as well. so you can see, so you can appreciate. I'm going to change from degrees to radians, and I'm going to compare the theta in radians in terms of the theta, in terms of sine of theta. Oh. Like that, sine of theta. And then you're going to see something interesting. Let's start, start at 0, right? And every 1 degree until we reach 45 degrees. And you'll be able to see that the angle in radians is going to be very similar to the sine rad. Why you didn't like it? Let's see why you didn't like it. Yeah, didn't like it. Radian. Let's see. Radian maybe? Yeah, radians. Okay, radians, not rad, radians. I'm writing theta with in the units of radians, right? What you have here, theta in degrees. And then what you're gonna have here is gonna be the sine of the angle in radians. And watch what happens. And by the way, I'm gonna put it here, percentage difference as well. So you can see, okay, how it compares, how good this approximation is. I'm taking the percentage difference between sine of theta and theta in radians. Times 100 divided by sine of theta. This one is not gonna work because I'm dividing by 0, okay? But if we do that for 1 degree, see the percentage difference here is very small, extremely small. Up to the 5th decimal place, you don't see any difference up to the 5th decimal place. If here is 0.01745, here is also 0.01745. If there is any difference, it's past the 6 decimal places. And the percentage difference tells you that 0.05% is very small, can be negligible, okay? As we increase the angle to 2 degrees, what's going to be the percentage difference? It's going to be 0.02% only difference. We keep on increasing, 3 degrees, 0.04%. Remember that I told you anything less than 10% is negligible, right? 0.08%, man, is orders of magnitude smaller than what we can accept. But the difference keep on increasing, right? Which is already expected because I told you for the small angles, this is an approximation for the small angles. As we keep on increasing, at 10 degrees, we have only 0.5% of a difference. Only 0.5% of a difference. Let's see. Let's keep on going. 15 degrees. 1% now, 1% difference for 14 degrees. And as we go to higher and higher angles, let's see, 30 degrees. 30 degrees, the percentage of difference is already almost 5%, 4.7. Okay. And so this small angle approximation works very well. Works very well up to, let's say, 44 degrees. Up to 44 degrees, you have 10% of difference only, okay? That's what I want you folks to realize. If we plot the sine of theta and theta, it's gonna be almost a straight line. Yeah, see that? Almost a straight line. It's gonna start curving around here, right? Let's see if we can fit a linear. Yeah, we can fit a straight line that is almost 1. Almost 1. if theta and sine of theta were exactly the same, you would get a straight line with a slope equal to 1. Okay? So are you convinced now that this approximation is a good one? Right? When we use this approximation, then we can use, in my equation right in here, alpha now can be, the angular acceleration can be written in terms of G over L times theta. Okay? And by the way, what I have to write here, I have to write not with equality sign, I have to write with an approximation sign. Remind you that this thing is approximation. Okay. What else can I do? Now, what do? I compare that with my simple harmonic motion equation. And by the way, this thing here can be rewritten in a slightly different way. Alpha L, like that. Okay, alpha L. Recall that remember the Hooke's law, right? Going back to Hooke's law. Going back to Hooke's law. We have the following. Okay. Minus kx is equal to mass times acceleration. Right? And I'm even going to invert. The positions here of those guys. Here you go. Mass times acceleration is equal to minus kx. Like that. And then we compare Hooke's law with what we just got for the simple pendulum. Okay? So the situation is like, here you go. Linear acceleration, angular acceleration. Linear position, angular position. The only difference is in terms of some constants, right? And okay. And I can even, here write that in terms of the torque, right? What we had for the torque before. That what we had that. Yeah, let's have that for this one here. It's better if we compare this one. But then I have to apply the approximation. I have to apply the approximation here. And what you see writing here, let's see. What you see writing here is exactly what you see writing here, right? And I'm going to even change the order here. The negatives go to the left, to the right side. The positive go to the left side, okay? I'm going to change the order here too. Angular acceleration, linear acceleration. Linear mass, angular mass, which is the moment of inertia. See that? I hate this thing. I do not know how to get rid of it. Gets in the way. Make changes, auto rewrite, keep text. Oh gosh. if folks know how to get rid of this thing here, let me know, okay? Keep source formatting, merge formatting. Oh, no, it didn't. Gosh, now it's in the way. I hate that. Let's see if I can. Okay, good. I got rid. Somehow I got rid of it. And then I'm going to get rid of this guy, right? All I did here to get from here to here, all I had to do is multiply by ML. ML, right? ML here. Here you go. So again, linear mass, angular mass, linear acceleration, angular acceleration, negative, negative, K, MLG. K is a constant, MLG is also constant. Linear position, angular position, right? Constant, constant. So those two equations that you see there, almost exactly the same, right? So let me put it under color code, in a color code format. The red K stands for MLG. The brown M stands for I, right? The blue parameters here are the position. This violet parameter here is acceleration. One is the linear acceleration, the other is angular acceleration. Because of this straightforward relationship, we can say that theta have exactly the same equation as x, right? Remember we calculated x before? Let's see here. I'm going to get x here for you. Deve ser o meu negócio que já chegou. Here you go, x. Remember, those are the equation of motion for simple harmonic motion. Okay, so here you go. Okay, so my linear position is my angular position, right? X naught here becomes theta naught. Cosine doesn't change. What was K for the linear case becomes MLG for the angular case. MLG, right? Wait a minute. Nope, not here. Here. MLG. What was M, lowercase m for the linear case becomes ML square. See that? KML. KMLG. KMLG. Lowercase m, I. That's what I'm doing here. Oh gosh, I'm doing the wrong way here. Here you go. I marked the wrong one, right? Here you go. This one goes downstairs here. Here you go. K, MLG, M, I, and I is ML square. All right, let's put that here, ML square. ML square. Memor. O que ele tá fazendo? Okay. Okay, so now can we simplify that? Yeah, we can simplify that. ML here cancel out with ML. We end up just with L downstairs, and that's the equation of motion for theta for the case of the simple pendulum. What about the velocity? velocity. Now we're going to have this angular velocity that I'm going to call it omega. Okay? The x naught turns out to be theta naught. The square root of k over m is going to be square root of g over L, just like we saw before. Right? Square root of g over L. What else? That's it, right? No need. And what about the acceleration? The acceleration here becomes angular acceleration. Square root of km becomes square root of g over, square root of g over L. K over m becomes g over L. And here are the equations of motion for our equations of motion for the simple pendulum. For the simple pendulum, let's get that. Here you go. I don't need that anymore. I don't need that anymore. That's the equation of motion for the simple pendulum. Let me make sure I didn't make any mistakes, right? Yeah. That's right. Oops. Yeah, there is a theta naught here. And I have to substitute that upstairs as well. They are completely different systems, but mathematically they are similar, right? One is the mass attached to a spring, and the other is a mass attached to a string. And yet, mathematically speaking, they behave in a very similar fashion, okay? And the same thing happens to the physical pendulum. We're running out of time here. Let's see, we have 2 more minutes to go. So let me just put here a table that compares uniform circular motion with simple harmonic motion. Oh gosh. And simple harmonic motion with the simple pendulum and with the physical pendulum. What the equations look like, okay? And that's the one here. Like that. Here you go. Table, table, table. UCM. R cosine of theta t, of theta as a function of t, right? V minus V naught, blah, blah, blah. Simple harmonic motion, x naught. Here's the radius of the circle. Here's the distance from the position of equilibrium. Okay. By the way, this omega here is this guy. I do not know why I put omega there. Better not use the omega so it doesn't get mixed up with the other omega. Simple pendulum. Okay. Here, angular velocity. And here for the physical pendulum that we didn't do, but the derivation is very similar to that of the simple pendulum, okay? Next time I will do the derivation for the physical pendulum. Any questions about that? We can stop right now, and I'm gonna have my office hours if you want to hang around, okay? I'll be here. So otherwise, see you on Wednesday for the exam. Thank you for being here.
Professor,
Yeah.
I had a question about the grade for lab 3, the one that you posted in our group folder.
Uh-huh.
I don't see the grade, like our grade yeah, the grade in the PDF for it that
What
you put,
what's your group number?
group 7.
Group 7.
Yeah.
Okay. So I did you're telling me that I didn't upload that? Is that what you're telling me?
No, you did upload the PDF, but I don't see my grade. And
Really?
instead, yeah, when I see grade, it says name question mark, but mine and my partner's name is on the group fold, like it's there.
Okay, let's see what's the problem here. That's group 7 that I have here.
Yeah.
Let's see. Okay, yeah, you don't see the grade. The grade was supposed to be here. Let me see
Yeah.
what happened. Okay, let me fix that again. Okay, I made a mistake when I was correcting. That's why you don't see the grade. Let me fix that.
Okay.
I know the reason for that. I didn't know when I did it. Let me stop sharing. Okay,
Mm-hmm.
and I'm going also to stop recording.